Okay, so hi everyone, my name's Alex, and this is going to be my first video. It may be a series of videos about things to do with computing. Now, since I just finished my first year at University of Computing, I thought I might do some videos related to that. You know, so say if you're a student doing computing or computer science, or maybe electronics as well, you might need help. I thought I'd do a series that might be able to help people, say they're doing their exams, or just want to know about computing and the subjects inside it. So the first topic that I'm going to talk about is logic gates, and this is more to do with the architecture side or electronic side with computing. And this is one that I'm genuinely interested in, the architecture, the computer architecture. So I thought I'd start with that and maybe go on to the enterprise programming, as I've already got some Pygame videos as well. So let's get started. So I've got logic gates. So the first logic gate I'm going to talk about is the AND logic gate. The AND logic gate is also called the conjunction gate, flipping chair, and it's seen as, it's sort of like an arrow pointing upwards but without the line, so it's just like the upside down of a V. And when you're writing Boolean algebra, it looks like that, but when dealing with a logic gate, it's called the AND gate, and it has two input gates and one output gate. The output can only be 1 or true. When you're dealing with Boolean algebra, 0 is false and 1 is true. So with an AND gate, for the output to be 1, both A and B have to be true, both of them have to be 1. So if you have A equals 1 and B equals 0 on an AND gate, the output will be 0. And as you can see on the table to the right, the truth table, you have A, B, Y. Y is the output and A and B are just the input values. So on the first one we have A is 1 and B is 1, then Y equals 1. This is because it's the AND gate, and for the AND gate output to be true, both of the input values have to be 1 or true. 1 is equal to true and 0 is equal to false. So as you can see, we've got a combination of 1 and 0, and since they're not both 1, the output can't be 1, and since we've got 0 and 1, since both of them aren't 1, the output can't be 1. And we've got 0 and 0, obviously, since the output is going to be 0, because neither of the input values are 1. So the second gate is the disjunction OR gate. The OR gate is called disjunction and is seen as, it's like a V shape when you're talking about it in electronic circuit terms. It's the same as the AND gate in terms of the input values, and there is also one output value, but the OR gate differs from the AND value, the AND gate, when it comes to the results, as when there is an A equals 1 and B equals 0 on an OR gate, the output will be 1. The output will always be 1 except for when both A and B equals 0. So it's like with AND, for both of them to be true, the output will be true. But with an OR gate, if one of them is true and one of them is false, or one of them is 1 and one of them is 0, the output will always be 1. The only time the output is 0 on an OR gate is when the inputs are 0. So as you can see, so the OR gate, it looks like a half crescent moon or a Doritos chip. It's got the A input value, the B input value, and then the output. So as you can see, you got A and B, 1 and 1, the output is 1. You got A1, B0, output is 1. A0, B is 1, the output is 1. A0 but B0, and the output is 0. So an OR gate can have either A or B can be true, and then the output is still 1. But if both of them are false, then it's false. So the third gate is the negation gate. The negation gate only has one value in the input and output values, and it basically just negates the value that is put into it. So if A equals 1, the output will be 0, and with the A equals 0, the output will be 1. It's seen as like a line going horizontally and then going down a tiny bit vertically. And it's also called an inverter, as it inverts the input. So invert just means changes it or opposes it. And it's shaped like a triangle with a little circle on the end. And this little circle on the end of the triangle represents the inverter. So that's what it means, the little circle at the end of the triangle, it inverts it. You'll also see the little circle on things called NAND gates and NOR gates, which is the opposite of AND gates and the opposite of OR gates. As you can see from the truth table, A equals 1, B equals 0, and A equals 0 and B equals 1. So it's just inverting or opposing the input value. I think this is the last gate. I think there's a couple more. I'm going to talk about the XOR and XNOR gates in the next video. So the next gate is the NAND gate, and as I've just said, the NAND gate is the opposite of the AND gate. So the output is 1 when A and B are both 0, or both of them are either 1 or 0. So the only time the output is 0 is when both inputs are 1, leading to the opposite of the AND gate. So with the AND gate, for the output to be 1, both of the inputs had to be 1. Now whereas with the AND gate it's the complete opposite, so the only time that the NAND gate output is false is when both A and B are 1. So as you can see, I'll first explain the little diagram. So you got A and B as the input, then you've got the normal AND gate, but what you've got here is the little circle, as I've explained before. Now this represents the inverter, or the NOT gate, and what it does is it takes the values and just inverts or opposes what the values are. So we've got, on the right we've got A equals 0, B equals 0, but the output equals 1. A is 0, B is 1, the output is 1. A is 1, B is 0, the output is 1. But when we get to the 1 and 1, the output is 0, because in the normal AND gate, if A and B were both to be 1, the output will be 1, and all of these will be 0. But since this is the NAND gate, and it is the opposite, all of these results will be the opposite of the AND gate. So the only time in the NAND gate that the value is false is when both of the input values are true. I think this is the last one? Yeah, that's the last one. I'll just go over it quickly again, very quickly. So you've got the conjunction AND gate. When you're doing this, both of the input values have to be true or 1 for the output to be 1. Just to clear it up again, true and 1 are the same exact thing. 0 and false are the same exact thing. It's just how it goes in Boolean algebra. As in 1 is true, 0 is false. So in conjunction in the AND gate, for the output to be 1, both inputs have to be 1. In the OR gate, either A or B can be 1 for the output to be true, but if both input values are 0, then the output is 0 as well, and it's represented by a little v. The negation is the opposite, so whatever you put in the input, the output will be the opposite of what the input is. So if the input is 1, the output will be 0, and if the output is 1, or the input is 0, then the output will be 1. And if the input is 1, then the output will be 0. And the negation is represented by a horizontal line with another vertical line after it, and it's called an inverter, and it's represented by a triangle with a little circle on the right to it. The NAND gate is the complete opposite to the AND gate, and it's drawn exactly the same, except you have a circle at the end of it which represents the negation or inverter, as it's the opposite of the AND gate. So with the NAND gate, for the outputs to be true, it's just the opposite of the AND gate, and since with the AND gate, the only way that the output could be true was if both values were 1, both input values were 1. Everything that doesn't have both input values as 1 is true, because that's the complete opposite of the AND gate. So in the NAND gate you have A and B equals 0, but the output is 1, because in the AND gate, if both A and B were 0, the output will be 0 as well. So it's the complete opposite of the AND gate. So as you can see in the NAND gate, we have both 1 and 1 of the input values. So A equals 1 and B equals 1, but the output is 0, because that's in the AND gate. If A and B were both 1, the output will be 1. And since it's the NAND gate, which is opposing the AND gate, it is the opposite. Oh, God. Ones and zeros, man. Just like 8 minutes of fully 1, 0, 1, 1, A, B, output. But this is my first video in logic gates. My second one will be explaining, I think, the NOR gate and the XOR gate and the XNOR gate, and then from that part I might just see where I go from there. I might talk about processor design, so things like RISC, so reduced instruction set computers, complex instruction set computers, or maybe memory management to do with paging. What else is there? RAM, internal RAM, different types of RAM, virtual memory. What else is there? I don't know, just if you actually watch this video and want me to cover anything, just put it in the comments or something. Or if you think I'm doing something not well, just dislike the video and tell me what I can do better. But yeah, thanks for watching. See ya. Bye.